Hello students, today we will continue with EMT. Topic is propagation of electromagnetic wave in conducting media. Please subscribe to the channel before beginning to listen to the lecture to avail free PDF notes and other facilities of fully solved model paper, etc. Let us begin. Propagation of electromagnetic wave in conducting media. That means today we will study how this electromagnetic wave behaves in a conducting media. In fact, electromagnetic wave declines or exponentially decays when it enters a conducting media. Let us start proving it. Here we have our famous Maxwell's equations, del dot D, where D is displacement current, is equal to rho. Rho is charge density, also known as Gauss law of electrostatics. The second equation, del dot B equal to 0, is known as Gauss law of magnetostatics. The third, curl E is equal to minus del B by del T, coming from Faraday's law of electromagnetic induction. Curl H equal to J plus del D by del T, the modified form of Ampere's circuital law. From these four equations, the first two equations are independent in nature. We will be requiring the third and fourth equation in order to find an expression which shows us how electromagnetic waves conduct in an conducting media. So let us assume, like, conducting media can also be sea, water, etc. Let us begin. Let us assume that the medium is linear, isotopic, and it is characterized by permittivity, permeability, conductivity, and the charge density is rho equal to 0 everywhere. This means that no charge or current is there nearby. Any initial distribution of charge within the conductor will die out and the charges will be remaining on the surface. So now for rho equal to 0, what will be the Maxwell's equations become? Suppose the question asked is, write Maxwell's equations in conducting media. So for conducting media, you will write rho equal to 0, D equal to epsilon E, B equal to mu H, and J equal to rho capital E. These values we will put in our Maxwell's equations. So now del dot D equal to rho. So D we will put epsilon E. So del dot E will become equal to 0. Second, del dot B equal to 0. B we will put mu H and del dot H becomes equal to 0. Third equation, we will put B equal to mu H. Equation becomes del cross E equal to minus mu del H by del T. Fourth equation, curl H is equal to J plus del D by del T. So J is sigma E plus D, we will write epsilon E. So the four Maxwell's equations, which you can see here on the screen, del dot E equal to 0, del dot H equal to 0, curl E equal to minus mu del H by del T, and curl H equal to sigma E plus epsilon del E by del T are there in conducting media. Now, we are going to derive an expression for electric field and magnetic field in conducting media. What we will do is we will take curl of Maxwell's third equation on either side, and we will use the mathematical formula curl of curl E is equal to gradient divergence E minus del 2E. With this mathematical formula, we will put it here on the left-hand side of the equation, and we get gradient divergence E minus del 2E is equal to minus mu del upon del T of curl H. Now, we will put the value of divergence E and curl H from Maxwell's equation. So del E is equal to 0 and curl H is equal to sigma E plus epsilon del E by del T. The moment we put these values in this equation, the equation reduces to del 2E is equal to minus mu epsilon del E by del T plus mu epsilon del 2E by del T2. Similarly, for the magnetic field, we get the equation del 2H minus mu sigma del H by del T minus mu epsilon del H2 by del T2. These two equations are the general wave equations for electric and magnetic field vector in an electromagnetic wave. And they can be asked in your exam that write the electric field equation in conducting media or the magnetic field equation in conducting media. It can be a small question. Next, when electromagnetic wave is moving in a conducting media, then the propagation vector, that means the vector that is responsible for propagation of this wave, is a complex number. Complex means I. That means it can be K is equal to alpha plus I beta, where alpha can be some real part and I beta that can be imaginary. So we have to prove that for a conducting media, this electromagnetic wave has a propagation constant vector in a complex form. So what do? We assume an EMT wave traveling across the x-axis and the electric vector along the y-axis and the magnetic vector along the z-axis. EMT. The two E and B are perpendicular to each other. Using this expression which we just derived, del 2E minus mu sigma del E by del T minus mu epsilon del 2E by del T2 is equal to 0. Now, in this equation, we will assume that the field varying fields are as exponential form, E equal to I omega t minus kx. Then solution of these two equations in general form are Ey is equal to E naught e to the power of I omega t minus kt and H is equal to H naught e to the power of I omega t minus kt. They are the general solutions of these two equations. Here, E naught and H naught are the complex amplitudes which are constant in space and time, and they are responsible for the propagation vector. Now, what we will do is we will differentiate these equations first as a general d by dx, then d2 by dt2, and put the values of their differential in these equations above to get the answer. So let us begin. First, we will differentiate this equation with respect to x using the formula d by dx of x to the power of n is equal to nx to the power of n minus 1. So here we have del E y by del x is equal to minus k e naught e to the power of I omega t minus kx. Now we take the second differential of this expression and we get del 2 ey by del x2 is equal to minus k into minus k e naught e to the power of I omega t minus kx. Now we will put the value of ey as e naught ey equal to e naught e to the power of I omega t minus kx here, so that the equation looks a bit simple in its form, and we get del 2 ey by del x2 equal to k square ey. Similarly, del Ey by del T is equal to plus I omega E naught e to the power of I omega T minus Kx. Putting these values in the equation, we get del 2 Ey by del T2 is equal to minus omega square Ey. Now, these three values we have. We have del 2 Ey by del x2, del Ey by del t, and del 2 Ey by del t2. These three values we will put in this expression. Once we put these three values in this expression, we find that the propagation constant comes as a complex form. It is consisting of a real part and it is consisting of an imaginary part. This question has been asked many times in section C, that prove that the propagation constant vector of an electromagnetic wave is complex in nature. Now we can further simplify the expression to derive few more constants. See, k is a complex number, so we can assume that k is equal to alpha plus I beta, where alpha is the real part and beta the imaginary part. And what we will do is, we will square the above expression using the formula a plus b whole square is equal to a square plus b square plus 2ab. Now, square of I is equal to minus 1. So, squaring this, we get k square is equal to alpha square minus beta square plus 2 alpha I beta. Now, here the real part is alpha square minus beta square, and the imaginary part is 2 alpha I beta. Sorry, this should be imaginary. Now, we compare equations 8 and 9 here. See, k square is equal to minus omega square mu epsilon plus I mu sigma omega, and k square is alpha square minus beta square plus 2 alpha I beta. So when we are comparing them, alpha square minus beta square is equal to minus omega square mu epsilon. These two are the real parts and these two are the imaginary parts here. This should be imaginary. Okay, then once we compare the real and imaginary parts, what we do is alpha is known as attenuation constant and beta is known as phase constant. Also, this formula alpha square plus beta square can also be written in this form. So, putting the value of alpha square minus beta square equal to minus omega square mu epsilon, that is the real part of this equation, because k is a complex quantity. We get alpha square plus beta square is equal to mu omega square epsilon into under root of 1 plus sigma square upon omega square epsilon square. Also, alpha is known as attenuation constant given by omega under root mu epsilon into 1 plus under root 1 plus sigma upon omega epsilon whole square divided by 2 whole to the power of half. And phase constant beta is equal to omega under root mu epsilon minus 1 plus under root 1 plus sigma upon omega epsilon square divided by 2 whole to the power of half. So what have we to remember for electromagnetic wave in conducting media is that the electric field equation in conducting media is given by del 2E minus mu sigma del E by del T minus mu epsilon del 2E upon del T2. Same pattern we have for the magnetic field, and the Maxwell's equations in conducting media will be obtained when we will put rho equal to 0. That is del E equal to 0, del H equal to 0, del cross E equal to minus mu del H by del T, and del cross H equal to sigma E plus epsilon del E by del T. Also, lastly, the propagation of this electromagnetic wave in a conducting media has a propagation constant vector which is complex in nature. That means it consists of real part and imaginary part. Thank you.